Welcome back. We're going to carry on with what we started before your short break. All right, so just to remind you, we are looking at momentum. We had a quick look at the definition, we had a quick look at the equation, and we had a quick look at the properties. Okay, so which object, so we have a question here, has more momentum? A big object moving slowly or a small object moving quickly? Now we've got to go, well, most of us will go probably the big object moving slowly, because in our minds, we have this picture that momentum means it's got to be fast, because we often hear we're gaining momentum, okay? Or when you think of something that's rolling down a hill, and you go, they gain momentum, and by that we mean they're going faster. Sometimes we'll use the momentum in terms of work. So maybe you're studying for an exam and you feel like you've gained momentum because you got a lot done. And then somebody disturbs you and you're like, oh, my momentum's finished. I'm going to have to just start again. Yeah, it's not quite the correct way of using the word momentum, but you're thinking about motion. So when we think of something moving slowly, we often think it doesn't have a lot of momentum. But this is where we've got to go, actually, momentum's not just dependent on the size of the object. It's also dependent on the velocity, okay? And we can't go, it's just dependent on velocity. It's dependent on the size. So when I look at this question and I go, the big object moving slowly or the small object moving quickly, I actually don't have enough information, because I need to know how big the object is and how slowly it's moving. I need to know how small the object is and how fast it's moving, because the two work together. They're not independent. And it's very possible that these will have exactly the same momentum. There's no reason why they can't. I need to know more information. I need to have values. Now, here, when I talk about more momentum, I'm talking about the magnitude of the momentum. The direction doesn't affect the amount of momentum. So they could be going in opposite directions, and that's fine. That's a direction thing. It doesn't affect the amount of momentum that we have, okay? So this is a little bit of a trick question, because I can't give a definite answer. There are too many bits of information I don't know, all right? So, definition. This is how we would write it out. The momentum of an object is the product. Remember I said that to you? It's the product of the mass and the velocity of the object. Please, you must learn your definitions. These are your easy marks in your exams, okay? And you won't get any marks if you go, momentum is the mass and velocity of an object. Remember I said to you, you've got to give me product. That word product is very important. The equation, P equals mv. The nice thing is, given to you on your information sheet, lowercase p. So P is momentum measured in kilogram meters per second. Be careful here, because we see this from time to time where you make that a big K. It's a lowercase k. So just be a little careful for me there, okay? M is mass measured in kilograms. This is a big one because we get a little confused sometimes. The SI unit for mass in physics is kilograms, because we're dealing with stuff we can see and touch and feel and that sort of thing. In chemistry, it's grams. All right, so be careful here. We must work in kilograms. Velocity, meters per second. So that also means that you've got to remember how to convert, because sometimes they're going to give you the velocity in kilograms, kilograms, my goodness, kilometers per hour. Okay, so I'm just going to do a quick thing for you over here. To go from kilometers per hour to meters per second, you must divide by 3.6. This is just an aside. So this is just something you can keep as on a back burner somewhere, okay? Because it might come up in vertical projectile motion, it might come up in work energy and power, but you need to be able to convert that, okay? So we divide by 3.6. I'm not going to worry too much about how we get there. Then, momentum is directly proportional, we've spoken about this already, to the mass of the object, okay? We cannot describe mass as being directly proportional to momentum because mass doesn't depend on momentum. Momentum depends on mass, okay? So the bigger the mass, the bigger the momentum. But remember I said to you, they change by the same factor. If I make the mass 3 times bigger, I'll make the momentum 3 times bigger. If I make the mass 10 times smaller, the momentum becomes 10 times smaller. Generally speaking, in our calculations, the mass of an object will remain constant. Okay, it makes our calculations a little bit easier. But the mass doesn't always have to stay constant. There are definitely situations where mass doesn't stay constant, like a rocket lifting off to go to space. It uses up its fuel, which makes it lighter. Okay, so mass is changing. But for us, in normal, everyday sort of situations, we assume mass remains constant, okay? Just to make our calculations easier. Velocity, momentum, is dependent on velocity. So if the velocity changes, momentum changes, but again, they're directly proportional. So that means for us that they change by the same factor. If I make the velocity 3 times bigger, the momentum is 3 times bigger. If I make the velocity 2 times smaller, the momentum's 2 times smaller. But what I need you to get here is the velocity we're talking about is going to be constant velocity. We are going to ignore the brief moment in time when if the velocity changes, there's acceleration. We're going to ignore that, okay? Because it makes the calculations very difficult. So we're going to look at situations where there's a velocity and then there's another velocity afterwards, but we're not going to worry too much about what happens in between at the beginning of this, okay? Because we want to keep it as constant velocity. So we're not going to look at situations which make it a little bit more real life. So for example, when you have an athlete running down a track, and say even Usain Bolt, who does the 100 meters in a ridiculous time, he doesn't run at a constant speed throughout the race. There's a speeding up as he starts the race, then he gets to a little bit of a constant velocity, probably speeds up again, or slows down. It all depends on the race. We're not going to worry about all those different changes. We would just assume that it's a constant velocity for the whole race. I know it's not completely real world, but we're just trying to get a concept across. We're trying to get the basic foundation of momentum. If you study physics further, then you'll do all the other stuff because then you've got the maths as well, okay? So, momentum is a vector. We hate vectors, I know. It's all right, we're good. What does that mean? Momentum has a direction. We've spoken about that. And the direction of the momentum now is the same as the velocity's direction. So if the velocity is east, the momentum is east. It gets its direction from the velocity of the object. You can't tell me that an object that's moving to the left has a momentum to the right, because that just doesn't work. okay, because momentum is about the velocity. So it's the same direction. And we can represent it by a vector diagram. So if I told you that we had a vector of 6 meters per second going east, and I wanted you to draw it as a diagram for me, what you would do is we have a line with our arrow, okay, and I put on it 6 meters per second. Now, I said to you in the last segment that we can't just assume to the right is east, and we can't. So I really need to be able to tell my examiner that I understand that that's north. Okay, so I know where the north is, and then that's east. You don't have to write the word east. Why? Because there's an arrow that's telling me it's going east. So just be careful with that one. Sometimes we want to put everything on there. We don't need to. Okay, the arrow direction tells me. I don't think, though it's not beyond the realm of possibility, that you will have to do these to scale, but you should be able to, okay? Also, if I'm drawing more than one momentum vector together, the relative sizes must be correct. So if I now tell you to draw a 3 kilogram-meter per momentum, also going to the east, it can't be the same size line. So if it's 3, it should be about half the size. Now, I didn't measure them. I did it visually, okay? So when we mark something like this, we just look at it and go, it looks about right. We're not going to take out a ruler and measure it. But it's the relative size, okay? That still needs to make sense because they're vectors, okay? So, lots again. So we went through the definition, the equation, and the properties. That means we need to do problems, okay? Because that's all the theory. We need to do problems. We're going to do that in the next section. So make sure you've got a calculator with you so you can do it with me. And we're going to take a short break, and I'll see you in a couple of minutes.